Welcome to 36 minutes of fascinating car facts, delivering a calm, steady voice to help you drift off to sleep. No loud noises, no sudden surprises, just interesting automotive knowledge to relax your mind. Whether you're a car enthusiast who finds comfort in mechanical details, or you simply need something engaging but soothing to listen to, you're in the right place. Get comfortable, close your eyes, and let's explore the fascinating world of automobiles together. Let's begin. The first automobile accident in history occurred in 1891 in Ohio. James William Lambert was driving one of his inventions when he hit a tree root, caused his car to swerve into a hitching post. Both Lambert and his passenger suffered minor injuries. This happened at a speed of probably less than 10 miles per hour. The first speeding ticket was issued in 1902 to a New York City taxi driver who was traveling at the breakneck speed of 12 miles per hour in a 5-mile-per-hour zone. The officer had to chase him down on a bicycle. Henry Ford did not invent the automobile, nor did he invent the assembly line. What he did invent was a moving assembly line for automobile production in 1913. This reduced the time to build a car from 12 hours to just 93 minutes. The Model T, which had cost $850 in 1908, dropped to just $260 by 1925. The Ford Model T was available in any color you wanted, as long as it was black. This wasn't a joke or marketing gimmick. Black paint dried faster than other colors, which was essential for the assembly line speed Ford wanted to achieve. By 1926, though, Ford began offering other colors as competitors were eating into his market share. Before cars had electric starters, you had to hand crank the engine to start it. This was dangerous. If the engine backfired, the crank could spin backwards and break your arm or wrist. Thousands of people were injured this way. The electric starter was invented by Charles Kettering in 1912 and first appeared in the 1912 Cadillac. It revolutionized driving, making it accessible to women and older individuals who couldn't safely hand crank an engine. The first car radio was invented in 1929 by two young men named William Lear and Elmer Wavering. They called their invention the Motorola, a combination of motor and Victrola. The radio cost $130, which was about one-third the cost of an entire car at the time. Despite the cost, it became incredibly popular because it gave people something to do during the long, boring drives of the era. Section 2, Engine Facts. The Boxer engine, also called a flat engine or horizontally opposed engine, is used by Subaru and Porsche. It's called a boxer engine because the pistons move in and out like boxers throwing punches. This design creates a lower center of gravity and better balance than traditional inline or V-configuration engines. The rotary engine, also known as the Wankel engine, has no pistons. Instead, it uses a triangular rotor that spins inside an oval-shaped chamber. Mazda is the only manufacturer that successfully mass-produced rotary engines. The RX-7 and RX-8 use this unique design. While smooth and high-revving, rotary engines are known for consuming oil and fuel and requiring frequent rebuilds. The most cylinders ever put in a production car engine is 16. The Bugatti Veyron uses a quad-turbocharged 8-liter W16 engine. This is essentially two V8 engines joined together. It produces over 1,000 horsepower and can push the car to speeds exceeding 250 miles per hour. Diesel engines don't use spark plugs. Instead, they compress air so much that it becomes hot enough to ignite the fuel. This compression ratio can be as high as 25-1, compared to about 10-1 in gasoline engines. This is why diesel engines are more efficient and produce more torque than gasoline engines. The term horsepower was coined by James Watt, the inventor of the steam engine. He calculated that a horse could do 33,000 foot-pounds of work per minute. 1 horsepower equals the ability to move 550 pounds 1 foot in 1 second. It's not a perfect comparison, and actual horses can produce more than 1 horsepower in short bursts. Turbochargers and superchargers both force more air into an engine, but they work differently. A turbocharger is powered by exhaust gases spinning a turbine. A supercharger is powered directly by the engine through a belt. Turbochargers are more efficient but have lag time. Superchargers provide instant boost but consume engine power to operate. Modern engines can run for 300,000 miles or more with proper maintenance. This is remarkable compared to engines from the 1960s and 70s, which often needed rebuilding by 100,000 miles. Better materials, tighter manufacturing tolerances, and improved lubricants have all contributed to this longevity. Section 3. Transmission Trivia. The first automatic transmission was invented in 1921 by a Canadian steam engineer named Alfred Horner Monroe. However, it wasn't until 1939 that General Motors introduced the first mass-produced automatic transmission, called the Hydra-Matic. It was available in the 1940 Oldsmobile. Manual transmissions are more efficient than automatics, but this gap has closed significantly. Modern automatic transmissions with 8, 9, or even 10 speeds can match or exceed the fuel economy of manuals. Continuously variable transmissions, or CVTs, can be even more efficient because they don't have fixed gear ratios. The clutch in a manual transmission uses friction to connect the engine to the transmission. It's made of materials similar to brake pads. A typical clutch can last anywhere from 30,000 to 150,000 miles, depending on driving style. Riding the clutch or slipping it excessively generates heat and wears it out faster. Double clutching is a technique where you shift to neutral, release the clutch, rev the engine to match the speed of the next gear, then shift into gear. This was necessary for old transmissions that didn't have synchronizers. Today's transmissions have synchros that match the gear speeds automatically, making double clutching unnecessary, except in heavy trucks or racing. The dual-clutch transmission combines the efficiency of a manual with the convenience of an automatic. It uses 2 separate clutches, one for odd gears and one for even gears. While you're driving in 3rd gear, the transmission preselects 4th gear, so the shift happens almost instantaneously. Volkswagen, Porsche, and other European manufacturers favor this design. Continuously variable transmissions use a belt or chain running between 2 variable diameter pulleys. By changing the diameter ratio between the pulleys, they can provide infinite gear ratios within their operating range. This allows the engine to run at its most efficient RPM regardless of vehicle speed. However, many drivers dislike the feel because there's no traditional shift sensation. The parking pawl is a small metal pin that locks your transmission when you put in park. It engages with a notch wheel connected to the transmission output shaft. If you park on a steep hill without using the parking brake, all the way the car rests on this small pin. Always use your parking brake to take the load off the parking pawl. Section 4. Brake and Tire Knowledge. Anti-lock brakes, or ABS, prevent your wheels from locking up during hard braking. They do this by rapidly pulsing the brakes, sometimes over 15 times per second. This maintains steering control and reduces stopping distance on most surfaces. The system was adapted from aircraft landing gear in the 1970s. Brake fluid is hygroscopic, which means it absorbs moisture from the air. Over time, this moisture lowers the boiling point of the brake fluid. If your brake fluid boils during hard braking, it creates air bubbles that compress, causing brake fade or complete brake failure. This is why brake fluid should be changed every 2 to 3 years. The first pneumatic tire was invented in 1888 by John Boyd Dunlop for his son's tricycle. Before this, vehicles used solid rubber tires that provide a harsh, uncomfortable ride. The air-filled tire revolutionized transportation by providing cushioning and better traction. Tire pressure increases as tires heat up from driving. A tire that's properly inflated when cold can gain 3 to 5 psi after driving for 20 minutes. This is normal and expected. Always check tire pressure when tires are cold for accurate readings. The numbers on your tire sidewall tell you everything about the tire. For example, 205/55 or 16 means the tire is 205 millimeters wide. The sidewall height is 55% of the width, or means radial construction, and 16 is the wheel diameter in inches. Tire tread is designed to channel water away from the contact patch. The grooves and sipes in the tread create paths for water to escape, preventing hydroplaning. This is why tire tread depth is critical for wet weather safety. Most states require at least 2 30-seconds of an inch of tread depth, but 3 30-seconds is much safer. Nitrogen in tires is used primarily in racing and aircraft. The main benefit is that nitrogen molecules are larger than oxygen molecules, so they leak out more slowly. Nitrogen also doesn't contain moisture. For normal driving, the benefits are minimal, and regular air works just fine if you check pressure monthly. Section 5. Fuel and combustion. Gasoline is a mixture of hundreds of different hydrocarbons refined from crude oil. The octane rating indicates the fuel's resistance to knocking or pre-ignition. Higher octane doesn't mean more power, unless your engine is designed to take advantage of it. Using premium fuel in a car designed for regular is just wasting money. Knock sensors in modern engines listen for pre-ignition or detonation. If they detect knocking, they retard the ignition timing to prevent engine damage. This is why modern engines can run on lower octane fuel than they're designed for, though it would reduce performance and efficiency. The air-fuel ratio for optimal combustion is about 14.7 to 1 by weight. This is called stoichiometric ratio. Engines run richer than this for more power or leaner for better fuel economy. But 14.7 to 1 provides complete combustion with minimal emissions. Fuel injectors spray fuel in a fine mist to mix with incoming air. They operate at pressures between 30 and 80 psi in port injection systems. Direct injection systems operate at over 2,000 psi. This high pressure creates an extremely fine mist that burns more completely. The catalytic converter uses precious metals like platinum, palladium, and rhodium to convert harmful emissions into less harmful substances. It turns carbon monoxide into carbon dioxide, hydrocarbons into carbon dioxide and water, and nitrogen oxides into nitrogen and oxygen. This is why catalytic converters are targets for thieves. The metals inside are valuable. Ethanol is added to gasoline in many regions, typically at 10% concentration called E10. Ethanol contains less energy than gasoline, so it slightly reduces fuel economy. It also attracts water and can damage certain rubber and plastic components in older vehicles. However, it burns cleaner and is renewable. Diesel fuel contains more energy per gallon than gasoline. This is why diesel vehicles typically get better fuel economy. Diesel also acts as a lubricant for the fuel injection system, unlike gasoline. Using gasoline in a diesel engine would star the injection pump lubrication and cause catastrophic damage. Section 6. Electrical systems. The battery in your car is a lead-acid battery, the same basic design that's been used for over 100 years. It consists of lead plates suspended in sulfuric acid. Chemical reactions create and store electrical energy. A typical car battery provides 12.6 volts when fully charged. The alternator generates electricity while the engine runs. It's called an alternator because it produces alternating current, which is then converted to direct current to charge the battery and power the vehicle's electrical systems. Early cars used DC generators, but alternators are lighter, more efficient, and more reliable. Your car's electrical system operates on direct current at 12 volts, but the alternator produces alternating current at varying voltages. The voltage regulator ensures the charging voltage stays between 13.5 and 14.5 volts to properly charge the battery without overcharging it. Spark plugs create an electrical arc that ignites the air-fuel mixture. This spark can be up to 40,000 volts in modern ignition systems. The spark jumps a gap of around 1 millimeter in about 1/10,000th of a second. Spark plugs fire millions of times over their lifetime. The ignition coil transforms the battery's 12 volts into the thousands of volts needed for the spark plug. Modern cars have coil-on plug systems where each spark plug has its own dedicated coil. Older cars use a single coil and distributor to send high voltage to each spark plug in sequence. The computer in your car, called the Engine Control Unit, or ECU, monitors hundreds of sensors and makes millions of calculations per second. It controls fuel injection, ignition timing, emission systems, and countless other functions. Modern luxury cars can have over 100 computers controlling everything from the engine to the seat heaters. The oxygen sensor in your exhaust measures the amount of oxygen in the exhaust gases. This tells the computer if the engine is running rich or lean, allowing it to adjust the fuel mixture for optimal efficiency and emissions. Modern cars have multiple oxygen sensors for precise control. Section 7. Cooling and lubrication. Engine coolant, also called antifreeze, serves multiple purposes. It prevents the coolant from freezing in winter and boiling in summer. It also contains corrosion inhibitors to protect the metal components in the cooling system. A 50-50 mix of coolant and water provides protection to about -34 degrees Fahrenheit. The thermostat is a simple mechanical valve that stays closed when the engine is cold and opens when it reaches operating temperature. This allows the engine to warm up quickly for better efficiency and emissions. Most engines operate between 180 and 210 degrees Fahrenheit. The water pump circulates coolant through the engine and radiator. It's typically driven by the serpentine belt or timing belt. When water pumps fail, they can leak coolant or make a grinding noise. Some engines have electric water pumps that can vary their speed based on cooling needs. Radiators transfer heat from the hot coolant to the air flowing through them. They consist of thin metal tubes surrounded by fins to maximize surface area. The radiator cap maintains pressure in the cooling system, which raises the boiling point of the coolant. A 15 psi radiator cap raises the boiling point to about 260 degrees Fahrenheit. Motor oil does more than just lubricate. It also helps cool the engine by carrying heat away from moving parts. It cleans by suspending dirt and combustion byproducts. It seals the small gaps between pistons and cylinder walls, and it protects against corrosion. Modern synthetic oils do all these jobs better than conventional oils. The viscosity rating of oil, like 5W30, tells you how thick the oil is. The W stands for winter. 5W means the oil flows like a 5-weight oil when cold. 30 means it flows like a 30-weight oil when hot. Multi-viscosity oils use additives that change behavior with temperature. The oil filter traps particles and contaminants as oil circulates through the engine. It contains filter media that can trap particles as small as 20 to 30 microns. The filter has a bypass valve that opens if the filter becomes clogged, allowing unfiltered oil to flow rather than starving the engine of lubrication. Section 8. Aerodynamics and Design. The coefficient of drag, or CD, measures how aerodynamic a vehicle is. A lower number means less air resistance. A typical modern sedan has a CD of around 0.3. The most aerodynamic production car, the Mercedes EQS, has a CD of just 0.2. By comparison, a brick has a CD of around 2.1. Aerodynamic drag increases with the square of speed. This means that doubling your speed quadruples the air resistance. This is why fuel economy drops significantly at highway speeds above 65 miles per hour. The engine has to work much harder to push through the air. Downforce is negative lift. Race cars use wings and underbody designs to create downforce, pushing the car onto the track for better grip at high speeds. The trade-off is increased drag, which reduces top speed. Race teams carefully balance downforce and drag for each track. The crumple zones in modern cars are designed to form in a controlled manner during a crash. This extends the time of the collision, reducing the peak forces experienced by occupants. The passenger compartment, however, is a rigid safety cell designed not to deform. This combination saves lives. Side mirrors create significant aerodynamic drag. This is why many modern cars have smaller mirrors, or even replace them with cameras. Removing side mirrors can improve fuel economy by up to 2% at highway speeds. The grille on a car isn't just for looks. It allows air to flow to the radiator for cooling. However, modern efficient engines don't need as much cooling. So many new cars have active grille shutters that close at highway speeds to reduce drag and improve aerodynamics. Underbody panels smooth the airflow into the car, reducing drag and improving fuel economy. Race cars take this to the extreme with completely flat underbodies. Production cars compromise between aerodynamics, cost, and the need to access components for service. Section 9. Safety Features. Seat belts save more lives than any other safety feature. The 3-point seat belt, which crosses your lap and shoulder, was invented by Volvo engineer Niels Bohlin in 1959. Volvo made the patent open and available to other manufacturers because they considered it too important to keep to themselves. Airbags deploy at speeds up to 200 miles per hour. They fully inflate in about 30 to 40 milliseconds. That's faster than you can blink. Sensors detect the deceleration of a crash and trigger the airbags before you've even moved forward in your seat. Modern cars have multiple airbags. Front airbags for driver and passenger, side airbags in seats, curtain airbags along the roof, and even knee airbags. High-end luxury cars can have 10 or more airbags. Each one is designed to protect specific body parts in different types of crashes. Electronic stability control uses individual wheel braking and sometimes engine power reduction to help keep the car under control. If the system detects that the car is starting to slide or spin, it intervenes automatically. This technology has prevented countless accidents and is now mandatory on all new cars. Collision avoidance systems use radar, LiDAR, or cameras to detect obstacles and potential collisions. They can warn the driver, apply the brakes automatically, or even steer to avoid a crash. These systems are becoming standard equipment on most new vehicles. Backup cameras became mandatory on all new cars sold in the United States in 2018. They significantly reduce backing accidents, especially those involving children who are too short to be seen in mirrors. The camera must activate whenever the vehicle is put in reverse. Crumple zones, airbags, and seat belts work together. The crumple zones extend the collision time. The seat belt restrains you and prevents ejection. The airbags cushion the impact. Each system depends on the others working properly. This is why it's critical to replace airbags after deployment and fix collision damage properly. Section 10. Manufacturing and Materials. Modern cars are assembled from thousands of individual parts. A typical car contains about 30,000 components. The supply chain required to manufacture cars is incredibly complex, with parts coming from suppliers all over the world. The body of most cars is made from steel, but aluminum is increasingly common to reduce weight. Some exotic cars use carbon fiber, which is extremely strong and light, but also expensive. The Honda NSX was the first production car with an all-aluminum body, introduced in 1990. High-strength steel allows manufacturers to make thinner, lighter parts that are still strong enough for crash protection. Advanced high-strength steels can be 3 times stronger than regular steel. This strength-to-weight improvement is critical for fuel economy and safety. Robots do most of the welding in modern car factories. A typical car body can have over 4,000 weld points. Robots can place these welds with perfect consistency and precision, which is important for structural integrity and crash performance. Paint isn't just for appearance. It protects the metal from corrosion. Modern car paint is applied in multiple layers: primer, base coat, and clear coat. The entire process takes place in carefully controlled environments to prevent dust and defects. The clear coat provides UV protection and gloss. Galvanizing is a process where steel is coated with zinc to prevent rust. Many modern cars use galvanized steel for body panels, which is why rust-through is much less common than it was decades ago. Some manufacturers offer rust-through warranties of 10 years or longer. Quality control in car manufacturing includes both automated checking and human inspection. Cars are tested on dynamometers, water tested for leaks, and driven through rough surfaces to detect squeaks and rattles. A small percentage of cars are taken completely apart to verify that assembly was done correctly. Section 11. Unusual and interesting facts. The average car contains about 25,000 pounds of materials. This includes steel, aluminum, plastic, rubber, glass, and various fluids. About 75% of a car by weight can be recycled at the end of its life. Car keys have evolved from simple metal keys to electronic fobs that communicate with the car. Modern keyless entry systems use encrypted radio signals. Some high-end cars use proximity sensing, where the car unlocks automatically when you approach with the key fob in your pocket. The new car smell that people find pleasant is actually the smell of volatile organic compounds off-gassing from plastics, adhesives, and upholstery. Manufacturers work to minimize these emissions because some compounds can be harmful in high concentrations. The smell fades as materials age and off-gassing decreases. The average American spends about 54 minutes per day driving. That's over 330 hours per year, or almost 14 full days behind the wheel. Over a lifetime, the average person will spend over 2 years inside their car. Windshield wipers were invented by Mary Anderson in 1903 after she noticed streetcar drivers had to open their windows in the rain to see. Her design was initially rejected by manufacturers who thought it would distract drivers, but it became standard equipment within a decade. Cruise control was invented by a blind man named Ralph Teeter in 1948. The story goes that he was frustrated by his lawyer's habit of speeding up and slowing down while talking. Teeter's mechanical cruise control maintained steady speed using centrifugal force and throttle position. The roads you drive on are designed with specific slopes for drainage. Roads are crowned in the center, so water runs to the sides. Curves are banked to help vehicles maintain grip while turning. The engineering that goes into road design is surprisingly complex. Section 12. Electrical and hybrid vehicles. Electric vehicles aren't new. In fact, electric cars were popular in the early 1900s, before gasoline cars became dominant. They were quieter, cleaner, and easier to operate than gasoline cars. The development of the electric starter and cheap gasoline led to their decline. Modern electric vehicles use lithium-ion batteries, the same technology in your laptop and phone, but scaled up massively. A Tesla Model S battery pack contains over 7,000 individual cells. These batteries can store around 100 kilowatt hours of energy, enough to power the average house for about 3 days. Regenerative braking in electric and hybrid vehicles captures the energy normally lost as heat during braking. The electric motor runs in reverse, acting as a generator to charge the battery. This improves efficiency by 10 to 25% in city driving. Hybrid vehicles combine a gasoline engine with an electric motor and battery. The electric motor can power the car alone at low speeds, assist the engine during acceleration, or capture energy during braking. The engine can run at its most efficient RPM or shut off completely when not needed. Electric motors produce maximum torque from 0 RPM. This is why electric vehicles accelerate so quickly. A gasoline engine has to build RPM to produce power, but an electric motor delivers full torque instantly. This instant response makes electric vehicles feel very quick even if their top speed is limited. Charging an electric vehicle takes longer than filling a gas tank, but most charging happens at home overnight. A typical 240-volt home charger can fully charge an electric vehicle in 4 to 8 hours. Fast public chargers can add 200 miles of range in 20 to 30 minutes. The range anxiety people feel about electric vehicles is becoming less of an issue as battery technology improves. Many modern electric vehicles can travel over 300 miles on a charge, which exceeds most people's daily driving needs. For longer trips, fast charging networks are expanding rapidly. Section 13. Racing and Performance. Formula One cars can pull lateral G-forces of up to 6 GS in corners. That's 6 times the force of gravity pressing the driver into the seat. The human body can only withstand this because of specialized training and because the forces are distributed across the body by the seat and harness. The engines in modern Formula One cars are 1.6-liter turbocharged V6s, yet they produce over 1,000 horsepower. They rev to 15,000 RPM and are among the most thermally efficient engines ever created, converting over 50% of fuel energy into mechanical work. Drag racing vehicles can accelerate so quickly that drivers experience over 5 GS. Top fuel dragsters reach over 330 miles per hour in less than 4 seconds, covering a quarter mile. The supercharged engines produce over 11,000 horsepower and consume about 15 gallons of nitromethane fuel per run. NASCAR vehicles look like stock cars but share very little with production vehicles. They use tube-frame chassis, carbureted V8 engines, and 4-speed manual transmissions. The body panels are shaped to match production cars, but are purpose-built for racing. Endurance racing, like the 24 Hours of Le Mans, tests reliability as much as speed. Cars must run at racing speeds for a full day with minimal maintenance. Manufacturers use these races to prove the durability of their technology. The Nürburgring Nordschleife in Germany is considered the ultimate test of a performance car. The track is 12.9 miles long with over 150 turns and significant elevation changes. Manufacturers use lap times at the Nürburgring as a benchmark for performance. Section 14. The Future of Cars. Autonomous vehicles use a combination of sensors to navigate. These include cameras for visual information, radar for detecting objects and measuring distance, LiDAR for creating three-dimensional maps, and GPS for positioning. The computer processes all this data to make driving decisions. Self-driving technology is categorized into levels from 0 to 5. Level 0 is no automation. Level 1 is basic features like cruise control. Level 2 includes systems like Tesla Autopilot that can steer and control speed but require driver monitoring. Level 5 will be full automation with no human input required. Connected car technology allows vehicles to communicate with each other and with infrastructure. Cars will warn each other about hazards, coordinate to reduce traffic congestion, or receive updates about traffic lights and road conditions. This vehicle-to-everything communication could significantly improve safety and efficiency. Hydrogen fuel cell vehicles generate electricity through a chemical reaction between hydrogen and oxygen. The only byproduct is water vapor. They can refuel in minutes like gasoline cars, but offer the efficiency and smoothness of electric vehicles. The main challenges are the cost of fuel cells and the lack of hydrogen refueling infrastructure. Three-dimensional printing is starting to be used in car manufacturing. It allows for complex shapes that would be difficult or impossible with traditional manufacturing. Some companies are printing entire car bodies or chassis in a single piece. As the technology improves, it could revolutionize how cars are designed and built. Biofuels made from plants can be used in existing gasoline and diesel engines with little or no modification. Ethanol and biodiesel are already in use. Advanced biofuels could be carbon neutral, as the carbon released when burning them was recently absorbed from the atmosphere by the plants. Section 15, Maintenance Wisdom. Regular oil changes are the single most important maintenance task for engine longevity. Oil lubricates moving parts, cleans contaminants, and helps cool the engine. As it ages, it breaks down and becomes less effective. Fresh oil keeps engines running smoothly for hundreds of thousands of miles. Tire rotation extends tire life by ensuring even wear. Front tires typically wear faster than rear tires because they handle steering and most of the braking. Rotating tires every 5,000 to 7,000 miles distributes the wear evenly across all four tires. Transmission fluid doesn't last forever, despite what some manufacturers claim. It breaks down over time and becomes contaminated with metal particles from wear. Regular transmission fluid changes can extend transmission life significantly. Most transmissions benefit from fluid changes every 30,000 to 60,000 miles. Air filters are simple but important. A clogged air filter restricts airflow to the engine, reducing power and fuel economy. Replacing the air filter is one of the easiest maintenance tasks you can do yourself and only takes a few minutes. Brake fluid absorbs moisture over time, which lowers its boiling point and can lead to brake fade or failure. Flushing brake fluid every 2 to 3 years maintains braking performance and prevents corrosion in the brake system. Coolant contains additives that prevent corrosion and maintain proper pH. These additives deplete over time, even though the coolant itself doesn't wear out. Regular coolant changes protect your engine and cooling system components from corrosion and damage. Battery terminals can corrode, creating resistance that prevents proper charging. Cleaning battery terminals and keeping them protected with a corrosion inhibitor ensures reliable starting and proper charging system function. Section 16, Closing Thoughts. Cars represent freedom and independence. They allow us to travel where we want, when we want. They've shaped our cities, our culture, and our economy. The personal automobile has been one of the most transformative technologies of the modern era. From the first horseless carriages to today's electric and autonomous vehicles, cars have continuously evolved. Each generation of technology has brought improvements in safety, efficiency, and capability. The cars of tomorrow will be cleaner, safer, and more connected than anything we drive today. The internal combustion engine has powered our world for over a century. While its era may be coming to an end, its impact will be felt for generations. The engineering lessons learned and the infrastructure built around it have shaped modern civilization. Maintaining a car is about more than just keeping it running. It's about taking care of something that takes care of you. A well-maintained vehicle is reliable, safe, and can last for decades. The time and money invested in maintenance is always less than the cost of neglect. Every car has a story. The memories of road trips, daily commutes, first dates, bringing home new babies. Cars are more than just transportation. They're part of our lives, witnesses to our journeys. As you drift off to sleep, perhaps you're thinking about your own car, or a car you once loved, or a dream car you hope to own someday. Whatever the case, rest peacefully knowing that these machines, these remarkable combinations of metal and engineering and human ingenuity, will be there tomorrow, ready to take you wherever you need to go. Sleep well, drive safely, and may your journeys always be smooth. Good night.